Let's take a look at an example where we can use what the ideal gas law says to make a prediction about the yield of a chemical reaction or the amount of a reactant that we need for a chemical reaction much faster based on what the ideal gas law tells us. This example corresponds to example 18.8 in your textbook and deals with volumes of reacting gases. The process in question we're going to talk about is an example of the Haber-Bosch process, which we touched on in Chapter 9. This is one of the most important industrial chemistry reactions in the world because the balanced chemical equation here describes the process by which atmospheric nitrogen is fixed so that you can put it into fertilizers in the form of ammonia. So ammonia is one of our most important fertilizers in industrial chemicals. If we want to synthesize ammonia on an industrial scale, suppose that a volume of 683 billion cubic feet, that's obviously a massive volume, of gaseous ammonia, vapor phase ammonia, at 25 degrees Celsius and 1 atmosphere external pressure is being manufactured. For the manufacturing process, we'd like to predict what volume of hydrogen gas, H2, under the same conditions would be required to prepare this amount of ammonia by reaction with N2. So our two tools to solve this problem are the balanced chemical equation that we've been given. 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas, H2, to give us 2 moles of ammonia, NH3. We can use the ideal gas law, as we know, to relate the number of moles of any of these gas phase chemicals to the volume that they would occupy at 25 degrees Celsius and 1 atmosphere of pressure. But now we can take this type of thinking even further to really shortcut the problem. The key thing to recognize to make this problem straightforward to solve in one step is that equal volumes of gases under the same temperature and pressure conditions, that's important, equal volumes of gases, if they're under the same temperature and pressure, must contain the same number of moles or molecules, because volume, according to the ideal gas law, is equal to N, the number of moles, times the gas constant, times T, the temperature, divided by P, the pressure. And what that means is, as long as temperature and pressure aren't changing, volume is directly proportional to number of moles. The V alpha N is math speak for volume is equal to a constant times the number of moles as long as temperature and pressure aren't changing. So as long as the temperature and the pressure stays the same, what the ideal gas law is really telling us is that for problems like this, we don't have to solve the ideal gas law explicitly to relate the volume of the gas to the number of moles. We can say as long as pressure and temperature don't change, volume reflects the number of moles. And so what we can say about moles, we can actually say about volume. Again, and this is the key thing, as long as the temperature and the pressure are not changing between the two gases that we're talking about. So instead of making a calculation based on moles, we can calculate the answer to this problem and use stoichiometry related to volume because volume is proportional to the number of moles. If I have 683 billion cubic feet of ammonia, then I would need 3 billion cubic feet of hydrogen gas, according to the chemical reaction, to react with 2 billion cubic feet of ammonia. Because according to the ideal gas law, with pressure and temperature being the same, what's true for moles will be true for volume. Volume indirectly reflects the number of moles. So we can actually, to solve this problem, use stoichiometric coefficients from the balanced chemical equation. But instead of working out how many moles of the gas we have, we can just say the same thing about volume. Because 1 mole of either gas will occupy the same volume at this temperature and pressure combination. So we can say that we can arrive at our answer by saying 683 billion cubic feet of ammonia. We'll need 3 billion. We start with 683 billion cubic feet of ammonia, and we will need 3 billion cubic feet of hydrogen to react with every 2 billion cubic feet of ammonia, giving us we need 1,025 billion cubic feet of hydrogen to fully react with 683 billion cubic feet of ammonia. According to the ideal gas law, as long as pressure and temperature are not changing, volume reflects the number of moles. So we can do this problem just knowing the volume of the gas that we started with. Checking out our sig figs, we would be entitled to, it's ambiguous here, but probably the 1 atmosphere is an exact pressure. 25 degrees Celsius, again, is probably an exact temperature. So the number of sig figs called for based on the problem setup is a little ambiguous here. I'm going to assume that we're entitled to 3 sig figs based on the 683 billion cubic feet measurement, because we should be able to measure atmospheric pressure and temperature to a greater degree of accuracy than 1 or 2 sig figs. So I'm going to keep 3 sig figs in my answer here, but you can make an argument for 2 or 1 sig fig. 1.03 times 10 to the third billion cubic feet of hydrogen are needed to complete this reaction. And so this is really the power of the ideal gas law on display. Now, as long as pressure and temperature are constant, we can think of the amount of a gas, not explicitly in terms of moles all the time, but we know that for a gas phase sample, volume is directly proportional to moles. And what we say about chemical reactions in the gas phase that we could say about moles for any chemical reaction, we can actually say about volumes as long as we're talking about gas phase reactions. So this is kind of a subtle point that maybe looks a little too easy, but think hard about this one for a second, because this is a very powerful tool. And if you don't see the connection here through the ideal gas law, make sure to ask about it, because it'll really make your gas phase problem solving quite a bit easier.